Hello, everybody, and welcome to another wonderful day of chemistry. So, today we are going to be starting a brand new chapter as we're going into chapter 3, where we're really going to be looking at how favorable something is. So, trying to evaluate whether or not something will occur. And for this, we're going to be talking about this in terms of spontaneity. So, does something happen on its own? So, for context, it's really important to remember that so far we've just been talking about enthalpy and internal energy. And this just indicates how stable a system is. And this is going to have a big influence on when something happens, but it isn't going to be the controlling feature. As we have many reactions that require energy, but still naturally occur. So the enthalpy and internal energy themselves do not tell me what system is more favorable. All it says is that energy has to be conserved. This is one of the reasons why we can often talk about reversible states, things going forwards and backwards, and we're able to use the same equations for expansion as we are for compression. So we need something a little bit more nuanced. So what we need to think about is, what do we know about the tendency of where energy wants to be? This is often expressed in the idea that energy tends to go from areas of high energy to areas of low energy. Because it turns out what energy really wants to do is it wants to disperse. So if I have a hot object and a cold object, it tends to go from areas of high thermal energy to areas of low thermal energy. Now we need to go ahead and find a good way of articulating this idea. And this is where we introduce something called the second law of thermodynamics. And there's multiple different ways we can go ahead and refer to this second law. We're going to start with two kind of historical perspectives of how we can talk about how favorable reaction is. The first one is just simply what we said, is that heat does not spontaneously go from a cool body to a warm body. So we don't have energy tending to go from areas of low energy to high energy. And you can tell from this definition that this is very much kind of an original classic thermodynamic definition. So we might want something a little more nuanced. Unfortunately, the next one we have is very classical thermodynamics in terms of how will it influence what I can do. And this is also still a very good idea. And this is the idea that if I'm going to take a heat source, I'm going to have it transfer energy. I can't take all of the energy from heat and turn it into usable work. I can never have a perfect conversion and put in 100 joules of heat and get 100 joules of work. The process will always be a little inefficient. Some of that heat is going to have to go uh, into a cold sink that will help drive the process. So the inherent favorability will be going from hot to cold and pulling some of that energy off as usable work along the way. So both of these are very good, but you'll notice they're also very specific to this classic thermodynamic processes of how energy and heat moves. So we might need something a little bit more robust and nuanced. And this is where we can go ahead and do exactly what physical chemists love to do and try and turn this statement of expression into an actual mathematical rule. And we do so by introducing a new state function called the entropy. And specifically, what we're going to be talking about is the entropy of an isolated system, which, as we saw with enthalpy, is another way of saying the entropy of the universe. So the idea here is the entropy of an isolated system has to increase if a reaction is spontaneous. So if a reaction is spontaneous or naturally occurs, the entropy has to increase. So if something happens, I immediately know what the sign of the total entropy is. If something never occurs, it's very likely going to have a negative total entropy. So any spontaneous process will always increase the entropy of the universe. And this is also another common way of expressing the second law. But what we can do now is we can take a look at this idea of entropy and now kind of really use the fact that it's a state function. So we know that the total entropy has to always be increasing. So any change in total entropy has to always have a positive sign. But we can do the same trick we did with enthalpy. We can break it up into the thing we care about, the system, and the thing we don't care about, the surroundings. And what this says is that we can have systems that will organize we can have processes that organize our system, where the system will have a negative entropy, but the surroundings will offset that by becoming even more entropic. So this really shows that the universe works kind of like a kid cleaning its room. I can go ahead and make my room more organized, just don't look in the closet. So next time, we're going to take a little bit of a diversion and take a break from classical thermodynamics to look at what entropy means on a statistical mechanical perspective. Until then, take care.